The goal is to introduce HDF5 just so we're on the same page. And we've had kind of like probably a smattering of people talking about HDF5 and kind of high level, but I kind of want to just to get us on the same page, go over HDF5 for people that don't know about HDF5 and for people that already have some experience with HDF5. This might be a review for you. I'll discuss the data model using HDF5, the programming model using HDF5, how you then, what we're interested here is parallel access using HDF5, and then some performance tuning hints using HDF5. So what is HDF5? It's basically a hierarchical data format. That's what HDF5 stands for. It started off as HDF without the 5, originally at NCSA at the University of Illinois. It started off at HDF4. HDF4 was the original implementation of HDF. And then we decided we needed a format change, so we came up with HDF5. The two are not really related. We do have translators. If you have HDF4 file, you can translate it to HDF5, but HDF5 is really its own thing. It's open file format. Anyone can design and help implement the file format. It's really meant for high volume, large simulations, and a way to organize complex data that you might have. It's open source. You can download it. You can modify it. You can redistribute it. You can do whatever you want with it. And then it's really a way to model your data. It's not just a way to write the data. You want to be able to model it by using structures and organizing it in a specific way that benefits your simulation. So what is HDF5 like? It's very similar to XML. It has, you can do it's self-describing. You can use extensible types. It has rich metadata that you can describe the data that you have in the file. You can also include binary files, binary parts. You can have for high performance. You can compress them. It's scalable. It's also very portable, like a PDF. So it's standardized. You can take it from one computer to another and still read the file. And it's very similar to how you would find on your file system. You have directories and files. It's very similar. So you'd have a collection of related informations. And it's similar to a database. It's not exactly, we don't have all the features and bells and whistles that you'd find in a database. But if you take this all together, we kind of take each part of this, and this is what an HDF5 file tries to mimic. It's really designed, as I said, for high volume, very complex data. We want it to be portable, and we want to handle each system. So you want to handle it, you can run it on your phone or you can run it on a supercomputer. It doesn't really matter what size computer you're running it on. We want it to be flexible. We want it to be efficient way of storing your data and getting it back. And we want to be able to evolve with the application. So if we find a new application, we want to be able to modify HDF5 to accommodate these new models that you might come up with. And then a major component is supporting long-term data. So if you want to preserve your data and have it read back in 50 years, our goal is to have that possible. So the HDF5 model, you can just think of a HDF file as a container. It just holds data objects that you might have. How you think of the HDF model is essentially on the left here. These are the fundamental concepts of HDF5. You have your data sets, you have your groups, and your attributes. I'll talk a little bit about what each of these mean later. And then you have your supporting objects that support your fundamental objects here on the right. And this is what's in an HDF5 file. So this is what when you look at the documentation, this is what the HDF5 operates on, these objects here. The first object then is the data set. It's just a way of usually storing like a multi-dimensional array. So here you have a 2D array, and you can have your third dimension here as time steps. So you can store this simulation in just one multi-dimensional array. So it's just a way to organize your data. And then, of course, you have to be able to, HDF5 is a self-describing format. So you want to be able to tell the person reading this what the data type, so in this case it could be a 32-bit integer. And you want to describe what the size of this multidimensional set is. So in this case, it's a rank 3 array, and the dimensions are 4 by 5, and you might have 7 time steps or something like that. So it's really a way to just organize and contain your data in a data set. So this is the data type, what's the type in the file, and the data space describes what's the array dimension. This is what I said before. You can have, for your data space, you can have a null space. You don't have to have anything in it. You can have a scalar, which is not very common. So if you wanted to just store a little piece of information about your data set or data space. And then the most common use of data space is to store this simple arrays. You can have it, you essentially have your rank, your dimension size, and you can also tell it the maximum size of this array. So you can either have an extendable, or you can just have a fixed sized array for your matrix. Data space really has 2 roles. It contains spatial information, so the rank and dimension about the array, and it's a permanent part of the data set, or it can be, or it can describe just a partial part of your data set. So you can see in green here, you have your whole data space. You can also define a subspace of this. Here is in green, so this would be just this is a rank 1 by 10, and you just want these elements. You could describe this as your data space. We have a wide variety of data types that we support. So we have integers, floats, enums, arrays. You can also define your own. We have a user-defined. If you have like satellite data, they're partial to storing 13-bit integers. You can do that. You can also have variable length, strings, vectors, compound or compound derived types. You can have really as complicated a data type as you have in your code. You can store it in HDF5. This is a simple example of what a data set would look like. So you have a 3 by 5 array. It's essentially integer. It has a value of 12 is stored in this element, and it's ranked 2 by 5, 3. So this is a simple one, and then you can go much more complicated for that. So if you take it now, you can have the same array, but instead of having a single atomic data point or data type, you can have a compound data type here. So here you have a compound data type of an unsigned int, a character, int32, and then you can also have another array, a subarray. So you can have, at each element, you can have this template of what this compound data type is. So how are these data elements stored? You can store them continuous. So if you have it in memory continuous, you can also store it in the file as continuous. Another concept in HDF5 is chunk data. So you have your full buffer in memory. You can chunk, so you can write little pieces of that array in little chunks. So each little part of that array will be set on the file system, and then of course we index to get the where each of those little chunks is stored. Chunked really helps with access time. So if your data model kind of mimics this kind of chunk data, it's good to have chunking in your data set. And that's also a way to extend the data set. So if you know that you want to extend like the time dimension, you want to keep extending it, you need to chunk the data set. And you can also have compression with the data set. Compression helps, of course, with the storage size and improves the efficiency. Yes?
So is there a reason you would want it contiguous rather than chunked?
Probably because it's simpler in the code to implement. That's the reason. I mean, you can't really extend it because, I mean, if you keep extending it, you're going to run into something else that you've already written. So you really can't extend a continuous data set. So we also have the third fundamental is attributes. So this basically is a metadata type thing that you can write. So you have a name and a value. It kind of decorates what an object is. the value kind of describes what the data, described by the data type and the data space. It's very similar to what a data set is, but it's really not meant to store large data sets. It's really meant to describe what's in the data set itself, not necessarily be part of the data set. So that's what attributes do. You can also have groups and links. So groups was a way to organize, and links was to organize your data. So if you have this model here, where you have essentially a root group, the slash, and you have, let's say you want to contain all your visualization in a certain group, so you call it viz, and then you want to have another part of your file that has the simulation data that you might have to access later, and you can also link. You can link outside different files, so you can, within a file, HDF file, you can link to another HDF file and have it read in by that, or you can have it linked to other parts in that file itself.
That's crazy. I didn't know you could go to another HDF file.
Yeah, you can link to another HDF5 file.
Wow.
So I'll go a little bit over the software now, HDF5. It's the home page you can see here. The latest release is 1.8.15. We're going to come up with the next release is early fall this year. And another major release we're working on is the 1.10, which I'll discuss a little bit about what features we're putting in it. That's a pretty exciting release. The source code can be downloaded from the web page. It's written in C, but it has C++, Fortran APIs, and high-level APIs. The high-level APIs are just simply, they're kind of wrappers for the low-level APIs that let you do stuff without getting into the nitty-gritty about how to create a data set. You could just say, create this data set, and it'll give you that data set back. We also have command line tools to work with the HDF5 files, H5 dump, H5 repack, H5 difference. You can, very similar to what you'd find in a Linux type of environment. And we have compile scripts. I'll talk about some of that later. You can also download pre-built binaries in C, C++, Fortran, to include all those libraries. You can find all that on the web page. Some will require the compression external libraries, szip and zlib. H5 dump is a tool to dump the HDF5 files. It just displays it on your screen, or you can dump it to an output file. H5cc, H5c++, H5fc, those are just scripts that compile applications. So if you just have an HDF5 file and you want to quickly, or an HDF5 program, you just want to quickly compile it and run it, you can use these scripts. I mean, normally what you would do is just, if you obviously have a make file or CMake file or something, and you'd put in where the header files in the libraries, the HDF5 libraries are found. But if you don't want to worry about that, you can just use these compile scripts. There's also a viewer that we have. It's very simple. It's not kind of a scientific visualization tool, but it's more of a what's in my file, and it's a Java app browser for the actual data. So if you just want to quickly look at what's in the file and not necessarily analyze it, HDF is a good tool to use. And we have many examples on our website in C, Fortran, Java, Python, MATLAB. You just take a look here, and all the slides are on the web, so you can just kind of go there at your leisure, look at the examples. So I'm going to next go over the programming model and APIs. So basically what your application sits up here. Let's see. So this is your application, and then you'll probably talk to either the HDF, you'll have an middle layer, H5 part, or some other high-level APIs, netcdf. This talks then again to the HDF5 library. You talk through the wrappers. Here's where you create your data, your groups, your data sets, your attributes. Then we have the internal parts of the library itself, handling the memory management, the writing the data. And then finally have however you're getting that data to disk, whether it's POSIX, here, or you're using some kind of MPI-IO, the HDF5 library handles that for you. And then at some point, you end up with a file, an HDF5 file. So like I said, we have all the wrappers. I'm in charge, actually, the Fortran, writing the Fortran wrappers for the HDF5 library. We also have IDL, MATLAB, Python. H5Py is really meant for if you want a wrapper of the C APIs, then H5Py is probably what you're looking for. There's also Py tables. The C routines begin with the prefix H5 and then question mark, and the question mark is what letter that means is what that is acting on what you plan to do with that data set. So D here is for if you want to, you're interfacing with the data set itself. H5F stands for files, so you want to do something with the HDF5 file, whether opening or closing it. And S, since D's been used, we do a dataspace. So if you're modifying or creating a dataspace, you would use those functions. And they're all organized in that's a similar manner. And of course, there's a lot of them. There's over 300 plus functions, but you don't have to really know them all, just like MPI. I mean, there's a lot of functions there you don't have to know. You can start off with the very simple ones, and then you can add to your program if you want to add more complexity or start tuning the I/O part of it. So the high level, the general programming flow is just to, you have an object, you open it or create it, you access this object, possibly you could do it over and over again, and then you close the object. So, and then finally, there's another option that you can use. You can use properties. You don't have to use them to access these objects, but they do such things as that allows you to chunk the storage. It gives you different types of I/O you can use for this storage. For parallel, you can use different types of output. It also gives you the chance to use different types of access properties. So in a very high level pseudocode, you would just kind of, create the file. If you don't already have one, if you have one, you'd use H5F to open it. You would create your data space, simple in this case. I'll discuss a little bit later. You then create your data file. You can then read your data set. You close your data set. You close your data space, and you close your file. That's kind of what, at the high level, what you would do. So data spaces is common functions you would use, Hyperslab or select elements, and I'll discuss those later. And you can also get information about what the data spaces are. Data types that describes what data you're writing into the data set. Groups, so if you want to create groups in your file to organize your data, you can do that using the H5G functions. You can write, which you probably should, attributes to what this data really means. You can put in units, whatever you want to describe what somebody might need it later to decipher what you have in this file. And then property lists, that's a way to access properties on the file itself. We'll just discuss that it's a little later. So some C examples. Again, these are what you'd use to compile these simple programs. So it'd be H5CC, H5FC, C++. Compile, you would just do these simple wrappers and then the source file themselves. So how to create a file, you would simply call H5 create. This is the name of the file you'd give it. This tells it to wipe away what's ever there, so you can overwrite what's in your file. This gives you back your file handle, and then you can close your file once you're done with it. And by the time you're done with it, you would just have in this file just a root group. So now what we want to do is create a data set in this file. In order to do that, you'd create this file again. You would set your dimensions. So if we want to write an array that's 4 by 6, and we created a simple data space, so it's rank 2. This tells you the rank, and then tells you what the dimensions are. And then the null, this is an option that says, well, set my maximum dimension to this matrix to what the current dimension of the matrix is. You then now create the data set using, and we'll call this data set A. This is and we tell it what what type of integer we have. We want our data type to be the data space. This tells us that we're writing that array. And then these are the properties that we just set to default. And we'll discuss this, what you can change these to later for the parallel part of the talk. And then you close everything. You always want to close what you open or create. So you close the data set, close the space, close the file. And when you're done with the file, done with this operation, you would have the slash, and then you have, of course, your data set under A in the file itself. Now, if you want to create another group, then you would use your file handle again that you got from your open file. So then you create this B, which would be now under the root group. Using the default properties, you close it again, and your file would look like this. You'd have your A data set, your 4x6 data set here under A. You'd have another group under B that's empty. If you use the H5 dump tool on this file, you would essentially see this is the name of the file. This is the group, so you have the root group. You have the data set A, and we didn't fill anything with the data set, so it's all 0. These are the dimensions of the data space, and this tells us that the maximum dimensions are the same as the original dimensions. And then you have your group B under your group data set. So this is the kind of output that H5 dump gives you. So now if we want to initialize our data and actually write something, do something interesting, we would essentially say, well, this is my data set. I'm going to write W data. It's the native, so it's an integer type, so we're writing it on the integer type of that machine. Now, if you do H5 dump, it will write the data, as you can see here. And it automatically picked up what kind of data that should be. So that's the kind of data that's on the machine. Now, if you want to write a partial part of that data set, something similar you do in later you'll see when you do in parallel. Say you just want to write one row of this data. So it's a total 4x6 matrix, but you want to just write this row. So how do you do that? You first have to tell HDF5 what this data set is described by in space. So for this, we refer to a subset as a selection. Or a Hyperslab selection. So if it's specified, if you set up this data space, it's only going to operate on this particular Hyperslab selection that you've said to operate on. There's two types of selections. There's a Hyperslab selection. You can have a regular Hyperslab, a very simple Hyperslab. You can have sets of operations to make these Hyperslabs. And the other one is a point selection. So the Hyperslab, essentially, if you have a matrix or an array, you say, this is my section that I want. If you have a point selection, you can go through each element and say, I want points from different parts of this array. For the most part, people use a Hyperslab selection more than a point selection. I can talk a little bit about the penalties for doing both. This talk will mostly focus on Hyperslab selection, especially in the terms of doing parallel I/O. So examples of a regular Hyperslab, since you have a full array here, you can define your Hyperslabs to be the colored regions. So these are regularly spaced blocks. You can also have it be continuous parts of a subset of this array. And you can also have kind of weird-looking shapes for the Hyperslabs. This may be useful if you have like AMR and you're refining in this area. You might have a selection that's kind of not regular. So everything is measured in terms of elements. How you describe your Hyperslabs, you have a start, so you have a location, the starting location of where this Hyperslab starts. Stride is the number of elements that separate each block. You also have a count, so you have the number of blocks that you're describing. And you also have a block size. So this is an example of what each of these would be for this type of problem. So there's two ways to describe a simple hyperslab. You can describe using several blocks, such as this. So you define a small little block, or you can define one big block out of this subsection. It really doesn't matter what you do, so you can choose the hyperslab that makes that your code is most convenient to describe it. So if your code likes to describe in this sub-region of one big block, you can do that. Or if you'd rather describe it as little blocks, you can do that too, because the library will put these little blocks together and will say, well, if you're doing MPIO, don't write every single little block. Our library is smart enough to know that, well, you're describing a continuous hyperslab here, so I'm going to put them all together for you and write it to disk that way. So you won't have a penalty if you do it either or. So if you want to write a row, so in memory space, you would select, in your memory, you would select this one part of the row. It's a 1D of size 6. In the file space, so the memory space is where your program's running. Where you want it in the file, you would say, well, I want my file to start here with a stride. Sorry. It's this large, and I want it to stride and count 6 directions with one block. So this would give you, so this processor would just write this section of the hyperslab. This is how you would do it in the code. So essentially, you'd define those starts, where the count, how many the elements you're going to write. The files. This now defines the file space that you're selecting, and then you would write this. So this is your memory space that you've defined. So this is the 1D array that you have defined in memory. This is the file space that you define where you want that 1D array written to in a file. This is just a little bit about the file format. If you're interested in getting to the nitty-gritty about what's the file format spec, you can go look at it. I probably wouldn't suggest you doing this, but if you want to write your own way to read an HDF file, you can just look at this file format specification and write your own code to do it. So, but you don't really need to do that. Some of the roadmaps, this is where I'll wrap up for this part of the talk, is we're looking at concurrency issues now. This is what we're working on coming up. So we have a single writer, multiple reader. So you can have it where a process is writing a HDF file, and then you can have other processors come in and then read what the other one has already written. So you can kind of, it'd be nice where you're running a simulation where you have certain files, you're writing it, a single reader writing it, and then you can go back with many processors to look at the data set as it's running. We also have a virtual object layer. May discuss a little bit about that later on. We also have virtual data sets. This would be in the next major release, where essentially you can write your data sets now if you want to write them in different files, but you'll have a master file that will look like, to the master file, when a reader reads it, it will look like it's just one HDF5 file. But the data set is actually split up into other files. So it's a way of writing multiple files, but have the post processors or whatever it looks like a single HDF5 file. And then we're also working on native HDF5. It's a client server. So say you have your HDF5 file somewhere sitting on some server. You can query like temperature. Give me the temperature at this point. That will go off on the client machine. It would go off to the server. The server would access it, and then it would just bring you back the data that you want to get from the server. So you don't have to download or store your whole HDF5 file. You can just kind of query it on your clients, and it will bring back and fill your buffer with the data that you requested. And we're always very interested in performance. I think every release we have some type of performance improvement to the HDF5 file. some of the performance we've been working on is scalable chunk. We're working on metadata aggregation. I think this past year we've been working on improving the metadata reading and writing. And I'll have examples of that, especially in parallel. We're looking at asynchronous I/O and variable length records, so we're improving the performance of those. We're also interested in looking at fault tolerance. So if your program crashes, we don't want the data to be corrupted. We want to be able to get the data back and have to restart the program. We're still working on the parallel I/O, improving the performance of that, and we're looking at auto-tuning. A lot of this is to get really good performance, especially on parallel. You have to tweak it, and it's not always easy to do. So we're trying to make it easier to find the parameters that gets you the best speed on the machine that you're running on. So that's what's currently on the road for HDF5. That's all for the serial. So any questions for this part of the talk? Yes?
What about compression?
What about?
Road compression?
If we can get funding for parallel compression, we would.
How about you speak to the challenges of parallel compression?
The problem is it's each file, when each processor, when each processor wants to do compression, you don't know where the end, each processor has to know where to write the next part of the data. But when you're compressing it, each processor doesn't necessarily know what part of that, where to stick that compression in the data set itself.
Could you just create flavors of HDF5 for communities where there are some communities where the data is known and it's of fixed size, and then you will know that it will extend from here to here, and you can start compressing because that's the size.
That's the size. Yes,
So flavors. I think flavors of HDF5 would allow enabling additional performance improvements or simplifications.
Yeah. I'm not the architecture guy, so I don't know a lot of details, but he knows, we know how to do it, we just don't have the funding to do it. So, and we're always willing to have patches if you have a way of doing it or you're doing it now.
When
it's feasible.
Unidata did NetCDF on top of HDF5, speaking of the flavor of HDF5, do you know what, if anything, they did to, because the Unidata model is simpler than the HDF5 model, what, if anything, did they do to take advantage of that? Maybe nothing at all, but.
I don't know.
Okay.
I know. Yes?
So regarding chunking, it seems like this is a good optimization that you can do, because you may need to chunk with different size, and that may depend on the computer you are running on.
Yes.
So is this something you are looking at?
It's up to the application really to decide what size chunk fits best for their data. You kind of have to play around with the chunk size and see what performs the best for you.
That may depend on the computer you are
Yes.
running.
Yep.
As well.
Yeah, it depends on, especially your parallel file system as well.
Are we going to do some examples later?
Yes. Parallel examples.